Hello YouTube. In this video we will be going over matrices. So let's try and introduce matrices. Recall that if this list over here is a basis of V and T is a linear transformation that maps elements from V to W, then for any arbitrary V in V we have that T of V is equal to this. Thus, if we know the values of T of V1 all the way to T of Vn, so the images of the basis vectors, the values of the basis vectors, the values of T acting upon the basis vectors, we can calculate T of V, the value of T of V, for any arbitrary vector in V. And matrices are used to efficiently store the data corresponding to our linear transformations in a manner that is efficient for computation and quite helpful for developing theory. So we give the following definition. Let m and n be positive integers. A rectangular array of scalars with m rows and n columns is a matrix of dimensions m by n. So this over here is some matrix M with scalar entries, and all of those entries, have the appropriate indices, so we can refer to the appropriate element in the matrix. So some A of ij is the element in the matrix at the ith row and the jth column, so somewhere here. Now, take some I from 1 to n, fix it. We have that T of Vi belongs to W due to T mapping elements from V to W. And if this list over here is a basis of W, then there exist unique scalars, which I will denote like this, with these indices over here, such that T of Vi can be expressed as this unique linear combination of the basis vectors. Here's my last basis vector missing, oh well. And the scalars next to the basis vectors we will store in the following manner in a matrix which we will call the matrix of T of our given linear transformation. So for example, for our T of Vi, ith column, we store these scalars in the ith column. As you can see, this index over here, I corresponds to the column we're in, and this is the first row, the jth row, the nth row. And this way we can retrieve T of Vi when we're given a matrix like this using, you can have this aid over here to help you remember. So in the rows, we have the basis vectors of our space where T of Vi lands. So this is how we retrieve T of Vi when given a matrix. And now we define the following. So let this list be a basis of V, and this list be a basis of W, and T some linear transformation from V to W. Now, let T of V of J be equal to this. So this is the unique linear combination of T of Vj expressed via the basis vectors of W. And I denote the scalars like this. So again, J corresponding to the jth column. So the matrix of T relative to the given bases of V and W, denoted like this, is this matrix over here. So for example, for T of V1, these are the appropriate scalars. So here's an example. Here's some linear transformation that grows from f to the power of 2 to f to the power of 3, so ordered pairs into ordered triplets of our scalars. The standard bases, so when no bases are given, just from the context, we can assume that they're referring to the standard bases of our spaces. So this is the standard basis of all the ordered pairs, and here's all the ordered triplets. So again, if we want to get the matrix of T relative to these bases, then we have to just see how T acts upon the basis vectors of our original space. So T of 1, 0, when we plug in x equals 1 and 0 equals y, and here we get this, and the same goes for the second basis vector, we get this. And now this gets stored in the first column, and this gets stored in the second column. And we end up with this matrix over here of dimensions 3 times 2. And this is the matrix for t relative to these bases. Now we can define matrix addition and scalar multiplication of matrices in a pretty natural and simple manner. So if you have two matrices, you just add up the corresponding entries and put them into a new matrix. So they have to be of the same dimensions for addition to make sense. So you just add up the corresponding entries and you get a new matrix, which is the sum of these two matrices. And for scalar multiplication, you just multiply all of the entries in the matrix via the scalar. And now, when we introduce these operations, we have that the following holds true. So if, for example, we take two linear transformations and we add them up, so function addition, and then we take the matrix of that function, well, then it's the same as if we first took the separate matrices and then added them up. Same goes for scalar multiplication. So you can, if you take your function, your linear transformation t, and get a new function by scalar multiplying the transformation t and then take the matrix of that, it's the same as if you had first taken the matrix of t and then just multiplied that matrix by your appropriate scalar. You're free to verify that these hold using, the definition of function addition and the definition of the matrices we just gave for some appropriate linear transformation. And now the space, this over here, so the matrices with scalar entries of dimension m rows and n columns with these appropriate operations. Now this space is a vector space. And now we move on to the real meat and bones of this whole thing, figuring out matrix multiplication. So due to our matrices, we want our matrices of our given linear transformations to correspond to those linear transformations, and we would like for matrix multiplication to correspond to, those matrices when you multiply them with another matrix to correspond to function composition, so to composition of linear transformations. So we want the following to hold. We want, if we have two linear transformations that we compose and everything's meaningful and I take the matrix of that composition, I want that to be equal to this multiplication over here. So we will calculate this for our linear transformations and we will define multiplication so that this holds. So let's look at how S of t, the composition, acts upon some arbitrary v. Well, v belongs to v and it can be expressed as a linear combination, and then due to t being linear we get this. So S acting upon this, t being linear, it gets past the scalars and it acts upon the basis vectors. And now S again, due to it being linear, it gets inside of this sum and skips the scalars and acts upon these vectors. So this composition, S of t, this linear transformation, is fully determined by these elements over here. So it's action upon the appropriate basis vectors. And now, what is t of some vj? Well, it's equal to this sum over here. So t of vj gets mapped to w in our case, and in w we have some basis of w, and we can express this t of vj as some unique linear combination like this. And now we apply S to this. So S acting upon this, again, S being linear, it gets inside of the sum and it acts upon the wk's, the basis vectors of w. And then we get this sum over here when we, again, the SWK's also the same reasoning as here. They get mapped to some vector space U with basis vectors U1 all the way to UP. So we get this sum over here. And now we have to use the following little trick identity to make the sum a bit more digestible for our needs. So Here I've written the general form of the sum we have here using a sum AK, BRK, and CR. And here I've written out how that sum would look. So we have A1 multiplying this sum over here, and then we add the next row and all the way to AM multiplying this over here. So we add up all of these rows. Now, this addition can also be done in a different manner. So in the first column, we always have C1. We will have A1 multiplying this B over here, and here we will have AM multiplying this. I could distribute C1 out of this and then just have the sum of these multiplied by C1. And so we will be, instead of adding up all of these rows, so in this sum we're kind of going this row plus this row all the way to the last row. Now we will just go column by column. So we will take our C1, for example, it will multiply this sum over here, then we will add up C2 multiplying this sum, so these B's again with the appropriate A's. All of these A's will multiply all of these elements inside. So once we apply that reasoning, we figure this out, we derive that this sum is actually the same as this sum. So here we have our C's, we go, C1, which multiplies the sum inside, which corresponds to this. So this sum, which is our sum here, is actually equal to this sum, and this form is much nicer for our needs. So using this, we rewrite this as, so ST of Vj will be equal to this sum over here. So now we have that ST of Vj is equal to some linear combination of the U's, which are the basis vectors of our final space in which we arrive, our big U. So we have written this as the unique linear combination of the basis vectors in U. And now we can store, so when we store the stuff for our linear transformations into a matrix, we focus on the scalars. So we look at the appropriate basis vector and we store the appropriate scalars next to that basis vector. In our case, this whole expression over here, the sum, is our scalar. So if I were to write out this as a column vector, column vector, just a column, a matrix, we get this. So for example, when r is equal to 1, so u1, our first basis vector, the corresponding scalar is this sum over here, where r gets replaced by 1 and k goes from 1 to m, and so on, all the way to p. So every st of Vj is of this form, so our matrix of our composition would look like this, where these are the appropriate column vectors. So this over here, just written as shorthand. Thus we arrive at the following definition of matrix multiplication, where this expression over here is the key. So how do we define multiplication? So we have two matrices. They have to be of the appropriate dimensions, in the sense that, for example, A is of dimensions p times m. Well, B has to be, for example, it has to link with the m over here. Those have to be the same for multiplication to make sense. So B has to be example of dimensions m times n. And now C, which is the product of these two matrices, is a matrix of dimensions p times n, such that the element located in the ith row and jth column of this matrix C is given by this expression. This is how matrix multiplication is defined. So you fix the ith row of your matrix A, and you fix the jth column of your matrix B, and then you go through the rows. So in the ith row, the first element gets multiplied with the first element in the jth column of B, and then you go through the row and go through the column, you multiply the appropriate values, and you add them up to get your C, which is located in the ith row and the jth column. So this is how we define matrix multiplication. And when we've done this, you feel free to verify that this expression now holds. So another definition. So let this be a basis of V, and V some vector in V. Well, then there exist these unique scalars such that V can be written as a unique linear combination of our basis vectors, and we will say that the matrix of our vector V is this matrix over here, so a column matrix, column vector, so where we just store the scalars. And now we have the following proposition, which captures the whole point of matrices and multiplication and their connection to linear transformations, such that, so if T is some linear transformation, and this is a basis of V, and W is a basis of W, then the matrix of when our linear transformation acts upon some arbitrary V in our vector space V, well, that is the same as if I were to take the matrix of T relative to all of those bases and the matrix of V, and I perform matrix multiplication. So the action of a linear transformation on V, we can capture that, we can get that by using matrix multiplication of the corresponding elements. So let's show that this holds. So M of V is equal to this. Now, T of V, so T acting upon V, again, is equal to this. And now we take the matrix of this. So the matrix of this is equal to, well, these are scalars, so there's the matrix operator doesn't do anything, so we just left with this sum over here. So we write it like this, with the summation notation. So now each of these is of this form. So it's the jth column. The jth column looks like this, and we add up all of this. So I multiply my appropriate scalar with this, we get this. And now when we sum up all of these, we get this matrix over here of dimension m times 1, where these sums are the entries of the matrix. So this is m of tv. Now let's look at m of t multiplied by m of v. So m of t, here's my matrix, here's my m of v, and let's use so since we know we will be using the summation, the definition of matrix multiplication to figure out what the ijth element of this matrix will be. When we take the product of these two, we will get a matrix of dimensions m times 1. So when I look at the ijth element, due to the result being m times 1, j will be equal to 1, due to it only having one column. So let's look at the element that's located in some ith row of this product, and look at the ith element of this over here, which we've already calculated. And if those two are the same for some arbitrary I, then it means that these two matrices, well, they're the same dimension, and they have all the same elements in the appropriate places. Thus, we can conclude that they're equal. So what's the ith element in this matrix over here? Well, you just take the ith row from here. You get some sum like this. So you fix your I fix my ith row, that makes my t of ir, and then I just add up all of those. So the ith sum in here, the ith row. Now for this, when we use the definition of matrix multiplication, we get the same sum when we use this over here. So I fix the ith row and the jth column. So when we use that on this, well, I fix the ith row from here, so I get my ti, and then the counter goes some L, for example, from 1 to n. And over here, this is the matrix of our vector containing these scalars, all x1 to xn. Well, the jth column here, there is only one column, so j is equal to 1. And then we just go through the scalars with L. So we get the same sums for the ith elements. Thus, we can conclude that the matrix of this is the same as the product of these two. Thus, linear transformations can now be represented by matrices, and their action is captured by a matrix multiplication. So to each linear transformation, there corresponds some matrix of it, depending on what basis we decide to fix for these two spaces. For if I pick different bases, then the representation of my linear transformation changes. It's like coordinate systems. When you pick a basis, you get one description of some point in space. If you pick another coordinate basis, you're referring to the same point, just the numbers are different, the distances. So that's what's happening here. And we've established that T acting upon V can be captured by matrix multiplication. So it's the same as if we acted upon, there's the correspondence here where this can be captured by the matrix of T acting upon the matrix of V. And yeah, that would be it for today. So those are matrices. The fundamental concepts of linear algebra are, again, vector spaces and linear transformations. Matrices are just a very handy and efficient and useful way of representing linear transformations and their actions, hence their introduction. But the fundamental concepts are still vector spaces and linear transformations. That's where our attention goes. These are just very useful computational and theoretical tools for further studying vector spaces and linear transformations. So yeah, that would be it for today. Hope this was somewhat useful and you learned something. Have a good one.